Good morning, everyone, and welcome back. Over the last two lectures, we have taken an incredible journey. We started with an orderly, predictable world of laminar flow, where we derived exact solutions, the parabolic velocity profile, Poisson's law, and the clean friction factor, which is F is equal to 64 over Reynolds number. So it was very beautiful, it was exact, and it gave us a deep. Then we crossed the Great Divide. We stepped into the chaotic, random world of turbulent flow. We learned about fluctuations, Reynolds stresses, the viscous sublayer, and how the flow structure is far more complex. And we hit a wall. We admitted that we cannot, from theory alone, derive simple equations for turbulent flow like we did for the laminar flow. So, where does that leave us? How do engineers actually design the pipelines, the ventilation ducts, and the water systems that our world depends upon? The answer is a powerful combination of dimensional analysis and experimental data. So, today in this particular section, we are going to see how this works, how we are going to take the complex problem of turbulent pipe flow and using the tools we have to organize it into a manageable practical framework. So we will introduce the concepts of major losses, minor losses, and the Moody chart and the hydraulic diameter. So by end of this lecture, you will have the tools to calculate the pressure drops and head losses in real world piping systems. So let us start with the most fundamental part, the losses that occur in long straight sections of the pipe. These are called as the major losses, denoted as HL major in the subscript. So even though we call them major, theory reminds us that this does not necessarily reflect their importance. In a system with many components, the minor losses can actually be larger than the major losses. So our goal is to find an expression for the pressure drop delta P in a horizontal pipe. So based on our discussion of turbulent flows, what parameters should delta P depend upon? Let us build the list. First is the pipe itself. So its diameter d, its length l, and the roughness of its walls, which we denote by epsilon e. Roughness matters now because of that thin viscous sublayer we talked about earlier. Then the second is the flow, the average velocity v. Third one is the fluid, its density rho and its viscosity mu. So for turbulent flow, the density is critically important because the turbulent shear stress involves momentum transfer of fluid masses. So we have delta P as the function of the velocity, diameter, the length L, the epsilon roughness, the mu viscosity, and the density rho. So there are seven variables. So now we apply the dimensional analysis as we learned in the dimensional analysis of fluid mechanics. So we can reduce these seven variables, which involve three fundamental dimensions, M, L, and T, down to four dimensionless groups, which is written over here in the form of an equation. So let look at the right hand side. We have the Reynolds number Re equals to rho Vd by mu. We have the length to diameter ratio L over D, and we have the relative roughness epsilon over D. So this is much richer description than we had for the laminar flow where density and roughness did not even appear. Now, here is a crucial logical step. It's reasonable to assume, and experiments confirm also, that the pressure drop should be directly proportional to the pipe length. If you double the pipe length, you should double the pressure drop also. The only way this can be true is if we factor out the L by D ratio dependence. So we write delta P over half rho V square is equal to L over D phi, a function of Reynolds number, and E by D roughness over diameter. So now we define the term on the left multiplied by D over L as a friction factor. This is the Darcy friction factor named after Henry Darcy, a 19th century French engineer. So friction factor F must be a function of the Reynolds number and E by D, epsilon over D, which is the pipe roughness over diameter. So we can rearrange it to get the most important equation for the pipe flow, which is delta P equals FL over D rho V square by 2. So for a horizontal pipe, the pressure drop is directly related to the head loss. Remember from the energy equation for a constant diameter pipe with fully developed flow, delta P over gamma equals to HL. So we get the Darcy-Weisbach equation as HL major equals to FL over D V square over 2G. So this is it. This single equation is the workhorse of pipe flow analysis. It tells us the major head loss depends on a friction factor F, the geometry of the pipe L over D ratio, and the velocity head V square over 2G. But the million-dollar question is, what is F? For laminar flow, we know the answer that F is equal to 64 over Reynolds number. It's exact and independent of the roughness. But for the turbulent flows, the function phi is the function of the Reynolds number, and E by D is complex and cannot be derived theoretically. It must be determined experimentally. Now, the Moody chart and the Coolbrook formula, this brings us to one of the most famous figures in all of fluid mechanics, the Moody chart, which is represented on this slide. So this chart, published by Lewis Moody in 1944, is the graphical representation of thousands of experimental data points correlating the friction factor F with the Reynolds number Re and the relative roughness E by D, epsilon over D. So let us walk through its features as described in the subsequent explanation. That first if we look on the left hand side in the laminar region for when the Reynolds number is less than 2100, you see a single straight line. That's for the F equals to 64 over Reynolds number. It is independent of roughness. This matches our theoretical result as described earlier. So now we move to the right into the turbulent region where Re Reynolds number is greater than 4000. You see a family of curves, each for a different relative roughnesses epsilon over d. So for smooth pipes, epsilon over d is equal to 0. This is the lowest curve. The F friction factor decreases with increasing Reynolds number, following what's called the smooth pipe law. But for the rough pipes, as Reynolds number increases, the curves eventually flatten out and becomes horizontal. This is the completely turbulent and wholly turbulent regime. In this regime, F is the function of epsilon by d only and is independent of Reynolds number. But why? Because at very high Reynolds number, the viscous sublayer becomes so thin that the wall roughness protrudes completely through it, dominating the flow resistance. Now, notice the gap in the middle between 2100 and 4000 Reynolds number. This is the transitional range. The chart is blank there because the flow in this region is unpredictable. It might be laminar or turbulent or an unsteady mix. We generally avoid designing systems to operate in this range. So, how do we actually use this chart? You need three things: the Reynolds number, the relative roughness, epsilon over d, and the chart itself. You find your Reynolds number on the horizontal axis, go up to the curve for your epsilon over d, then go to the left to read the friction factor F on the vertical axis. So it's very straightforward. But in the age of computers, we often prefer equations. The experimental data on the Moody chart is well represented by the Coolbrook formula, which is hereby represented as 1 over under root f equals to minus 2 log of epsilon over d by 3.7 plus 2.51 divided by Reynolds number under root f. So this is an empirical equation that covers the entire turbulent range. But there is one catch, that f appears on both sides. So it's an implicit equation. You need to iterate to solve it. That's why the Moody chart was so valuable before computers. It gave you the answer without iteration. Now, for quick explicit calculations, you have the Haaland equation as represented over this slide, which is a very good approximation and can be solved directly for the friction factor F. Now, where do we get the roughness epsilon? The table, as shown over here, gives equivalent roughness values for common engineering materials. Notice the units are in feet and millimeters. Riveted steel can be very rough. Concrete varies. Drawn tubing, like copper tubing, is nearly smooth, and the plastic and glass are considerably hydraulically smooth, with epsilon value as 0. A critical point over here is that these values are for new clean pipes. As the pipes age, corrosion and scale buildup can increase the effective roughness dramatically, sometimes by an order of magnitude. This is an important consideration for long-term system design. Now, coming towards the minor losses, alright, we have covered the straight pipes, but real piping systems are full of other components like valves, elbows, tees, expansions, contractions, etc. These components also cause head loss, which we call minor losses, denoted as HL minor. And the name minor can be misleading. In a system with many fittings, these losses can be the dominant ones. Now look at this particular figure showing the flow through a valve. The flow path is tortuous. There are regions of separation, swirling motions, and intense turbulence. Analyzing this theoretically is virtually impossible. So once again, we turn to experiment and dimensional analysis. The most common way to represent these losses is with a loss coefficient, hereby denoted as KL, which is defined as the ratio of the delta P to half rho V square. So the head loss through a component is simply KL times the velocity head, as represented by this equation, which is HL minor must be equal to KL V square over 2G. So for most practical applications, especially at high Reynolds number, the flow through these components is dominated by inertia, not viscosity. This means the loss coefficient is primarily a function of the component's geometry only and is independent of the Reynolds number. So this simplifies things enormously. Now let us look at some common examples in your textbook. Entrance losses. This particular figure shows different types of pipe entrances from a reservoir. A re-entrant entrance pipe protruding into the tank has a high KL of about zero point 0.8. A sharp-edged entrance has KL of about zero point 0.5. This is due to the vena contracta effect as shown in figure. So the fluid cannot turn the sharp corner, so it separates, creating a high velocity jet that later dissipates the energy. A slightly rounded reduces KL to about zero point 0.2. A well-rounded entrance can get KL as low as zero point zero 0.04. So the lesson over here is that a little care in design can significantly reduce the losses. But what for the exit losses? Here the figure shows that the pipe exits into a reservoir. Regardless of the exit geometry, re-entrant, sharp-edged or rounded, the loss coefficient is KL, has a value of 1. Why? Because the kinetic energy of the fluid leaving the pipe is completely dissipated as it mixes in the large reservoir. That entire velocity head is lost. Now, for sudden expansions and contractions, these two figures show loss coefficients for sudden area changes. Now, for a sudden contraction, KL depends upon the area ratio and is less than zero point 0.5. But for the sudden expansion process, there is actually a theoretical result from applying momentum and energy equations. The loss coefficient is KL equals to 1 minus A1 over A2 whole square based on the upstream velocity. Now for the diffusers and nozzles, this figure shows that expanding a flow gradually, a diffuser is very tricky. If the diffuser angle is too large, the flow separates, causing huge losses. There is an optimum angle around 8 degree for minimum loss. This shows how difficult it is to decelerate a flow efficiently. Conversely, accelerating a flow in a nozzle is much easier and has very low losses. Now, for bends and fittings, these two figures represent the losses in the bends. A smooth 90-degree bend has losses due to secondary flows and separation. A sharp metered bend has a much higher loss, which can be reduced by adding the guiding vanes. Finally, this particular table is your go-to reference for many loss coefficients for standard components like threaded and flanged elbows, T's, and various valves. Notice that how a wide open globe valve has a KL value of 10, which is huge, while a fully open gate valve is only 0.15, and a swing check valve has an infinite KL for backward flow. It's a one-way device. This table is incredibly useful for real-world designs. Now, for non-circular conduits and hydraulic diameter, what if your pipe is not round? What if it's a rectangular duct for heating and cooling or an annular space? So this particular section gives you a powerful tool to handle the hydraulic diameter DH. The idea is to define the characteristic length that represents the size of any cross section, defined as DH equals to 4 times area divided by the wetted perimeter. So where the P is the wetted parameter and the length of the solid boundary in contact with the fluid. So for circular pipes, area must be equal to pi d square by 4 with uh, P is equal to pi times diameter. So dH for circular pipes would be equal to the simple diameter of that particular pipe. The factor of 4 is chosen specifically. Now, for non-circular ducts, we can use the hydraulic diameter in place of the diameter in all our key equations for now. Reynolds number rho VDH by mu, relative roughness equals to epsilon over dH, and head loss as HL equals to FL over dH V square over 2G. So for laminar flow, in non-circular ducts, the friction factor can still be written as F is equal to C over Reynolds hydraulic Reynolds number, where C is the constant that depends on the shape, which can be found out by the table as represented. So for a rectangle with an aspect ratio of 2:1, C is about 62, not too far from 64. But for a very thin slot where A over B ratio approaches zero, the C approaches 96. So the shape matters. But the hydraulic diameter concept allows us to use a similar form. For turbulent flow, this particular section, we can use the Modi chart directly with the hydraulic diameter, and it's usually accurate to within about 15%. For most engineering works, that's acceptable. If you need more accuracy, you need a detailed analysis for that specific shape. So let us bring this all together. Today we built the practical toolkit for analyzing the pipe flow. We used the dimensional analysis to define the friction factor F, which encapsulates the complex physics of turbulent flow into a single parameter that depends on Reynolds number and the relative roughness. We introduced the Darcy-Weisbach equation, which is HL equals to FL over dV square over 2G for calculating the major losses in the straight pipes. We also learned to use the Moody chart and the Coolbrook formula to find the friction factor F. Then we defined the minor losses using loss coefficients KL for components like valves, elbows, and entrances, giving you the table as a key reference. And we also extended all of this to non-round ducts using the concept of hydraulic diameter DH. You now have all the tools to calculate the total head loss in a pipe system. Next time, we are going to put these tools to work, we will dive into the next section and solve the real world problems, determining the pressure draws, finding flow rates, and sizing the pipes. We will work through examples that show exactly how to apply these equations. So for now, get comfortable with the Moody chart, understand where the laminar line comes from, what the rough pipe curves mean, and how to use the tables. So this is the foundation for everything that follows. See you next time.